Good morning, students. The next topic from Unit 4, what we are going to discuss today is that is constrained least square image restoration. So here first we want to know about what is the constrained least square filter. After that, how the algorithm of designing the constrained least square filter with correspond to degradation model is discussed. So first we can see what is mean by constraint least square filter. So actually constraint least square filter it is proposed by Hunt 20 years ago. It is a linear image restoration technique. Saying about this, it is a linear image restoration technique. Image the smoothness of the restored image is maximized subject to a constraint on the fidelity of the restored image. Here, the smoothness of the restored image is maximized subject to a constraint on the fidelity of the restored image. So, when we say about fidelity, you can say the degree of exactness, the degree of exactness with which something is copied or removed, reproduced, copied or reproduced. That we can say it as fidelity. So, here, the effect of information loss in the degree can often be mitigated by constraining the restoration. Through this constraint, the through this constraint, the effect of information loss in the degraded image is balanced. It is optimized. Constraints have the effect of adding information to the restoration process. So when we say about the constraint restoration, it can be refers to the process of obtaining a meaningful restoration by biasing the solution toward the minimizer of some specified constraint function. So next to say about the constraint least mean square filter, it provides additional difficulty. So when we are saying about Bateman filter, due to the presence of noise, due to the presence of uh, noise in the uncreated image, both for normal image and degraded image, the power spectra should be calculated. That is very difficult, which was done in the Wiener filter. So, and another thing, a constant estimate of the ratio of power spectra is not always a suitable solution. That will not be a suitable solution in all the circumstances. So, to work on that here in constant least square filter, the knowledge of mean and variance of noise is taken. So, here, what's the thing? Instead of power spectra, we have taken the mean and variance of the noise. Mean and variance of the noise. That is sufficient to design this constraint least square filter. These parameters usually can be calculated from a given degree. So this is an important advantage. Here there is no need of original image. The algorithm present in the constraint least square filter has the notable feature that it yields an optimal result for each image to which it is applied. So now we want to design the constraint least square filter. Here we can use the degradation model. What we have framework. The degradation model can be used to derive the constraint least square filter. So considering the degradation one, it's very special domain that you can say g of x comma y is equal to f of x comma y convolution h of x comma y not zeta of x comma y. That is noise. So in matrix form, if you want to say g is equal to h of f plus zeta. So like this, from this constraint, we will be deciding the transfer function. The constraint least square filter transfer function. So what is the thing? The problem for creating the constraint is that is the sensitivity of H to noise, the sensitivity of the system filters function to noise. So one way to elevate the noise sensitive problem is to base optimality of restoration on a measure of smoothness, such as second derivative of image that we can say it is Laplacian function. To be meaningful, the restoration must be constrained by the parameters of the problem at hand. Thus, what is desired is to find minimum of a criterion function C defined as C is equal to summation x is equal to 0 to m minus 1, y is equal to 0 to m minus 1. So, with this limit, this is the range of all the pixel values in the image f of that derivative we are taking the second derivative Laplacian means it will the second derivative that will have an in-depth analysis of the image noise image noise. So with that the noise detail subject we can frame out the constraint, we can find out the constraint. This constraint is used in the transfer function. So the expression, the transfer function expression for to find out the restoration filter function is given by that is input that is the output image is equal to transfer function into input image. So with this concept we have frame out the expression where this be the transfer function of the this be the transfer function of the filter where gamma is a power that must be adjusted so that the constraint is satisfied. What is the constraint we require? It is automatically satisfied. So here the gamma, if you want to say gamma is a parameter that must be adjusted so that the constraint is overcome. And P of u comma v is the Fourier transform of the function that is constraint function. That is, we can say if you want to say in matrix P of x comma y is equal to 0 minus 1 0 minus 1 4 minus 1 0 minus 1 0. So this is the associated to constraint function. So when we are seeing about this function, this controls the this controls the problem generated due to sensitivity of noise in the system. So this will help to reduce the loss of information. This will reduce to reduce the loss of information. Thus, the constraint can be expressed as h conjugate of u comma v by modulus of u comma v whole square plus gamma modulus of p of u comma v whole square. Here is adjusted such that the resultant output will be a better resultant output. Thank you.